All right. All right. Hello, everyone. So welcome back after the short break. Um, yeah, back to compilers. I know lots of you have been working on compilers all along, looking at Marmoset. Assignment 3 is done. Lots of groups are submitting lots of solutions for assignment 4. So great. All right, and I'm going to be moving on to code generation, or I have been starting to talk about code generation, right? And so, well, before the baby break, so last Wednesday, a week ago, we started looking at the assembly language that we're going to generate, x86 assembly language, and I talked about, some ancient history and the different variants of x86. The registers we have basically 8 registers that we can use, the segment registers that you ignore. And then I started talking about, the most essential x86 instructions that you're going to need to generate code. And I got all the way to the move instruction. And this is an instruction that can do lots of things, relative to, say, RISC instruction sets like MIPS that you might have seen in CS241. Right there, you would have a bunch of different instructions to read from memory into a register, or from a register into memory, or to copy from a register to another register. So in x86, sort of the move instruction does all of those things. Okay, so I give you a whole bunch of examples of the move instruction, and now I want to move on to other move. Yes, that's move instruction. I want to move away from the move instruction to other instructions. If there's questions about move or about any of the sort of introductory stuff, the registers, do ask questions. All right. Okay, so enough move. So, after you move data around, you probably want to do some arithmetic, right? Or you're going to need to implement arithmetic for your compiler. So you get the sort of the instructions that you might expect. So an add instruction, and so you can add 2 registers, and there's some flexibility about add. You can also add constants and things like that. So much like move allows you to do all sorts of things, add does as well. But the basic form that you'll typically use is with registers. And one thing that might seem weird is that add only takes 2 registers and not 3, right? 2 operands and 1 result. And this is a common feature of many instructions in x86, is that they only take 2 operands. And so the, and I wrote it, oh no, that's right, okay. So the effect of this add instruction is like the plus equals operator in C and C++ and Java. So the idea is that you add EAX to EBX, and then the result always goes into the left operand. Okay, so most of the x86 instructions are designed this way. They only take 2 operands, and so the first operand is both one of the operands and also the destination. Okay, so that's how you can add 32-bit numbers. And there's a subtract instruction that works the same way. Okay, I'm using EAX and EBX as examples, but you can use any registers that you want here in these instructions, which might seem obvious to you, but it wasn't back in 1978. There's lots of instructions, especially in the 16-bit instruction set, that take very specific registers. Okay, but these ones are fine. Whatever register has the value that you need, you can do arithmetic on it. Okay, and then there's a multiply instruction, which again, back in the 70s and 80s, lots of processors didn't have multiply instructions. So you got to build a multiply with a for loop implemented in assembly language. So that was lots of fun. But, you're in luck. The 32-bit x86, you get a multiply instruction. The I, in general, says it's a signed operation. So without the I, you would do an unsigned multiply or an unsigned divide that we'll see next. For Java, all of your arithmetic operations are signed, and so you'll always use the I mul and I div. Okay. So if you want to divide two numbers, you can use idiv. And now it gets weird, right? Because idiv only takes a single register. And so this is an example of where x86 is weird. Right? So the 16-bit x86 instruction set was even more weird. There were lots more instructions like this. But in the 32-bit division still retains this. And so, what this does, I'll sort of put an arrow up here for the comment. All right, so idiv takes one register, so in this example, EBX. And what this will do is it will divide a 32-bit number in EAX and, EDX and EAX. It'll divide it by EBX, and it'll assign it to EAX. All right, so that's the operation that you get. So this register, you can choose any register that you want. That's what you're dividing by. But the divisor or the dividend, which one's which? The dividend, right, is always in EDX and EAX, and it's treated as a 64-bit number. So you can, even in the 32-bit instruction set, you can divide 64-bit numbers. So the high order bits are in EDX and the low order bits in EAX. Okay, and then the quotient, the result, always goes into EAX. So this is one instruction where you don't have a choice of which registers the operands have to be in. So if you want to divide, you have to get the numbers into the right registers. Now, while you're at it, while you're dividing, you'll get the quotient. You will also get the remainder, and the remainder always goes in EDX. Okay, so you basically get the remainder for free with that one instruction. So whether you're implementing Java division or Java remainder, use idiv, but you have to get the dividend into the right registers, and your quotient, has to end up in EAX and the remainder in EDX. Okay, so now if you're implementing Java, right, you only ever want to divide 32-bit numbers, so you really only care about EAX. So what do you put in EDX? And this is where people always think, oh yeah, I gotta set EDX to 0. Okay, and I got a question. All right, so the colon. So right, okay, I should explain this better. So we're gonna use 64 bits to represent the dividend. and each of these registers is a 32-bit register. Okay, so this colon notation, this means I have a 64-bit number, and I put the first 32 bits in EDX and the last 32 bits in EAX. Okay, so let's say 64-bit. Right? Okay, and so if I only have a 32-bit number, I'm going to put it in EAX, but what do I put in EDX? And, of course, the first instinct is to always put 0 in EDX, right? So you put 32 0 bits, and then your 32 actual bits you put as the last 32 of your 64 bits. But okay, and I wouldn't be talking about it if it wasn't a trick question, right, or a trick issue. The issue is if EAX is a negative number, right? So a negative number is going to start with a 1 bit. So the first bit of the 32 bits in EX is going to be a 1 bit. And if you make EDX all zeros, then the overall 64-bit number is going to be a positive number. Okay. So the point is, before you do a division, you need to set all the bits of EDX to match the sign bit of EAX, right? The first bit of EAX. And you could try to do that manually, but luckily there's an instruction that does it for you, and it's called CDQ. And so what this special instruction does is it copies the sign bit of EAX into all bits of EDX. Oops. Okay. And maybe it's not really that important what it does. The important thing is, always do this before a division, right? If you want to do a 32-bit division, well, you put your dividend in EAX, then you run the CDQ instruction, and that will set EDX correctly based on the sign of the number that you're dividing, and then you can do your IDiv instruction. Okay, so always do this right before a division. That's the key thing to remember. But what it does is it sets up EDX correctly for you. Okay, any other questions on division or on arithmetic or anything? All right, so I know the questions are delayed a little bit, so put in your questions and they'll come in and then I'll answer them. Okay, so we've got arithmetic. So what more do you need, right? I just need to implement JUICE, so I can move data around between memory registers. I can do arithmetic. I even don't have to implement long division myself, like I used to have to in the 80s. But what else do we need? So we need like go-tos and conditional branches and things like that, right? We're gonna need to implement control flow, like if statements and while loops. Okay, so in terms of branches, so there's a jump instruction, JMP, and it takes an address. Typically, you would use a label, right? You wouldn't hard code a number as the address, although I suppose you could, but typically you would use a label, and then I talked about labels last time, right? So somewhere else in your program, you say label colon, and then the assembler associates that label with the address of the instruction that comes after the label. And so then you do jump label, and that address will get loaded into the program counter, which is called the instruction pointer in x86. So it'll get loaded into the program counter, and execution will continue there. Right? So that's like a go-to instruction. And this one is unconditional, so it always jumps to that address. for if statements and while loops, you're going to frequently need conditional jumps. And so the way that this is done in x86 is by a pair of instructions. So there's a comp or comparison instruction. And again, you can give it two registers. And there's various other versions with constants and stuff. So you say, I want to compare EAX and EBX. I want to compare the values in those two registers. And the way this instruction works is that there's a separate register with flags in it, so with single bits that keep track of, where these two values equal. Was one of them larger than the other? Was one of them larger than the other when interpreted as a signed number or as an unsigned number? And so you do this comparison instruction, and then it keeps track of all of that information in these individual bits in the flags register. Okay, and then afterwards, I can use an instruction like this, like JE. So this jumps to a label, if EAX and EBX were equal. So, oops, I should if, right? If EAX equals EBX. All right, so if the two registers were equal, the comparison instruction would set a flag, and then the jump equal instruction checks that flag and will jump if the two were equal. And then there's a bunch of related instructions that do other things. So jump not equal, J and E. And again, you would typically use it with a label. And so this is if they're not equal, right? So that will jump if they're not, if EX and EBX were not equal when you compared them. And then for less than, greater than comparisons, so there's jump greater or equal, jump less, and jump less or equal. Okay, so I can say greater, equal, less, and less or equal. So again, they go based on the comparison instruction that you did, right? So if EAX was greater than EBX, then JG would jump in that case. All right. And these instructions all do a signed comparison. And then there's also unsigned versions of these. And the sort of way to remember them is it's JA for jump above. So if EAX is above EBX. So then there's jump above or equal, and then there's jump below and jump below or equal, JBE. Okay, and so these guys are unsigned comparisons. All right, so for Java, you'll typically want to do signed comparisons, so JG and JL. But for some things, if you're comparing addresses or something, you might want unsigned comparisons as well. All right. Or for chars, I guess, if you're ever comparing chars. Okay, so that's how you can implement jumps to go to a different part of the program, and conditional jumps to implement if statements and loops. And now there's a few more control transfer instructions, so a few more sort of jump-like instructions. But do ask questions if you have questions here. Okay. So what other instructions? So in addition to jumps, there are also call and return instructions. and they use the stack. So let me sort of take a step to the side here and talk about the stack. So there are explicit push and pop instructions that do what you would expect, right? You would push the value of a register on top of the stack. You would pop a value off the top of the stack into a given register. So push and pop, so they're hard-coded as instructions, and they're hard-coded to use the ESP register as the stack pointer. Okay, so it's not like MIPS where you get to implement your stack yourself with whatever register you want. These instructions always use ESP as the stack pointer. So, that's why even though you get 8 registers, you're pretty much stuck using ESP as the stack pointer. Okay, so now that we have a stack, so why is it important that the stack is hard-coded? Well, because procedure calls are also hard-coded. So there's a call instruction, and so you can use it with a label. So like the jump instruction, it will transfer control to the code at the address that you call. But before that, it's going to push the current program counter onto the stack. So it's going to push the EIP. So EIP is the x86 name for the program counter. Okay, so you can it's a register, but it's not a register that you would normally access. So it pushes the value of the program counter onto the stack, and it does a jump to the label. So it already includes a jump to the label. So it loads the address into the program counter. Okay, so you would use this to call a procedure, right? You would save the program counter so that you can return to it later, and then you would transfer control to that procedure. And then there's a ret instruction that is effectively popping the address from the stack into the program counter. So when you're done your procedure, you use ret, and it pops the program counter, takes you back to where you called the procedure from. All right. So again, if there's questions on those, do ask them. And then I have one more weird control transfer instruction, and that's int. So int stands for interrupt, and again, interrupts are sort of historically a hardware thing that we had in the 16-bit x86, and then they evolved in the later versions of x86. But the idea was that when different hardware wanted to get the processor's attention, it would cause an interrupt, and the processor would transfer control to some code at some specific address. And x86, in addition to those hardware interrupts, it also has software interrupts, and these are an instruction that you can execute to get the processor to transfer control to some defined memory location. And in this case, we're going to use this for a system call. And so the interrupt instruction takes an operand, and for us, that operand is always going to be 80 in hexadecimal. So the number 128, but we usually write it in hexadecimal 0x80. And this instruction is going to do a system call. All right, and so if you took operating systems, you know all about system calls. So the idea is you execute this instruction to tell the operating system, hey, do something for me, right? It's like a call into the operating system to get it to do whatever you want. And the way you tell it what you want to do is by putting the appropriate values in various registers. Okay, so in some of the links from the course website, there's a reference guide to the various system calls in Linux, at least. So you know the various operations that you can ask the operating system to do for you. In your case, sort of the most important one, or really the only one that you pretty much need to worry about, is the exit system call. So if I want to exit my program, I need to set EAX to the value 1, and that that designates the exit system call. If I set it to a different number, that would cause the operating system to do something else. And then EBX is going to be the return value from your program. All right, so this is the return value that you want to pass back to the shell, so that you want to pass back to Marmoset. So, if you remember, up until now, your compiler has been returning like 0 or 42. And so this is the return value that your machine language code is going to pass back to the operating system. Okay, and so in the assignment, there's various specified return values that you have to return, like 13 for if the Juice program would have thrown an exception and things like that. So the point is, you put the value 1 into EAX, you put the value, whatever your return value is, into EBX, then you execute this interrupt instruction, and control transfers to the operating system. And in this case, the operating system is going to stop your program with that specified return value. Okay. And one thing that is provided with the Juice standard library. Okay, and I've got a relevant question here. Okay, so let me answer the question first, and then I'll go back to this. So the question is, will we be linking against libc? Right. So libc is the standard library that implements, sort of the basic functions of the C language, and things like printf and I don't know, whatever you do in C programs, right? And it implements, say, printf in terms of system calls. So no, we won't be linking against libc, right? So you don't get to use all of these built-in C functions, but we will link against a really baby libc, and by baby I mean I printed it out and it fits on one page, but I mean you don't have to copy it down from the YouTube thing. It's the file runtime.s that is included in the standard library. So the Juice standard library, right? It has a whole pile of Java files that you've been compiling so far, and it has one assembly language file called runtime.s, and that is our standard library. And it's actually a good example of assembly language code, right? I've got all the various instructions that you might want to use on the board here, but sometimes it's nice to have an actual example of an actual assembly language file. So I'm giving you that one, and it has some small functions for allocating memory. So again, it'll ask the operating system, hey, give me some memory. It has the exit instruction as well, and it has the implementation of the write native method, right? So some people were asking about this native method in the Juice standard library. So there's a method that outputs one character to the standard output, and that is used in the Juice standard library to implement print line. Okay, and so that native method, that write native method, is implemented in this runtime.s. It's about, I don't know, 8 lines of assembly language instructions, and basically it calls the relevant system call to output one character to the standard output. Okay, so do read that runtime.s. One as an example of a little bit of x86 code, but secondly as the list of things that are given to you, that you can call from your generated code. Okay, so there's little bits of code, and you can just call them with the call instruction. They typically end with a ret, so they'll return to you when they're done. And there's comments, so to tell you what the code does. Okay, so do look at runtime.s, but you'll see lots of examples of system calls in there. Okay, so those are our control transfer instructions, right? So interrupt, call, return, and then the various jumps that, all of these cause the CPU to run, different code than the next instruction in memory. Okay, any more questions on these control transfer instructions? Okay, so in addition to actual assembly language instructions that get translated to machine language and that gets executed by the processor, sometimes you also want to give instructions to the assembler. So assembler directives. And on the course website, there's also a link to some documentation on the NASM assembler, which is the assembler that we're using. So, you can find a manual that will give you a list of all the directives. I think it also has a list of all the x86 instructions. So there's lots of information there. I just want to highlight sort of the most important ones. So one thing you might want to do is put your generated code into multiple files. Maybe one file per class. You don't have to, but I think it's convenient to do that so that you can, easily find your code and you can debug one file at a time and so on. Now, if you have your assembly language code in multiple files, then by default, any labels that you use in one file are only visible inside that file and not in any other files. So there's the global directive. So, global, it kind of looks like an x86 assembly language instruction, but really it's an instruction to the assembler, not to the processor. And this makes the label visible in other files. So I'm going to write, export label, because if you still remember your MIPS assembly from CS241, I mean, sort of the MIPS equivalent to global is export. So this makes the label usable in other files, but it's not visible in other files by default. If you want to use the label in a specific file, you have to say extern label. And so this is the equivalent of import. Right? So in MIPS, you would say export to make the label visible throughout the whole program, and then import to say, in this file, I want to be able to use this particular global label, so I want to import it there. So you would use extern to import it, and global to export it, to make it visible. Okay, so those are two important ones if you're generating multiple files. The other thing you typically want to do is insert constants into the generated code. So for example, you might do this to implement variables, right? You would use a label to give a name to a memory location. And then at that memory location, you want the assembler to not put any specific x86 instruction, but you want to literally put a number like 1, 2, 3, 4, right, as a 32-bit integer. So the DD instruction, the D stands for data, and the other D stands for a double word. So this is the equivalent of dot word in MIPS. So again, if you remember MIPS still, this tells the assembler, I want to take this number, encode it as a 32-bit integer, and put those 32 bits in memory right here, instead of whatever instruction would go there instead. So if you put a label before a DD, now you have 32 bits of memory. They're initialized to whatever value you want, and you can refer to them using the address that's in that label. All right. The D, I said, means double word. And in x86, the word means 16 bits. Okay, and that comes from the 1970s when x86, used to be a 16-bit instruction set. But even when it moved to 32-bit registers and then 64-bit registers, the sort of all the documentation, all the assemblers, all the assembly language use the word to mean 16 bits. And so then double word means a 32-bit word, and a quad word. So, if you wanted a 64-bit word, you would use DQ for a quad word. Okay, and there's other, if you just want 1 byte, you can do DB and so on. Okay, but these are to put constants in your code. And all right, maybe I'll squeeze one more in here. So I mentioned DB. So DB puts a byte as a constant into the generated code. So you could do DB42, and it would encode that as a byte. But often DB, you would use it with a string. So you can use DB to insert a string constant. And so it would take each character of your string and encode it as 1 byte. So this would generate 5 bytes in the machine language file, with the representation of those ASCII characters. Okay, so that's how you can, put a string constant into your generated code. Okay. All right. So that's how you can put constants. Right. So if there's questions, do ask. And then I've got just one more assembler directive, but it's a very important one. But go ahead and ask your questions. All right, we'll get rid of move here. Okay, so there's one more important one, and that's section. And typically you would say section text or section data. Okay, and I mean, there's others that you could do, but these are the two essential ones. All right, so what would you do with these? So these are assembler directives that tell the assembler that the what comes after the directive is either code, right? So code, so instructions, and or read, write data. All right. So, I mean, all these instructions that I've been talking about, you should always put them after a line that says section.text. And then I mentioned, you can use DD to create yourself a variable. If you do that, you should put a section.data before that. And you can put as many of these as you want in your file. So if you want to mix code and data, you just do section.text, put a bit of code, section.data, put a bit of data, then do section.text again, and you can switch between them. All right. But what these do is they mark them in the executable file. So they mark those addresses in the executable file as being, code or data. And then depending on the operating system, but pretty much, all of the operating systems that you're going to use nowadays, depending on the operating system, it's actually going to enforce that there's only code in the code section and only data in the data section. And in particular, if you were to try to, it'll prevent you from modifying the code, right? Because that's probably a bug. And so your program will crash if you try to modify the code. And on the flip side, it'll prevent you from executing the data, right? So this is a security feature, right? For, not for your JUICE compiler, but in general, hackers will try to, do buffer overflow attacks where they feed whatever server or whatever program you're running, some big long string, and it overflows your buffer, and then it overwrites some code with the data that they gave you, or maybe they arrange for the program counter to get the address of some data and try to execute the data that they gave you, right, to hack into your program. So this is a security feature that prevents the CPU from executing, if the program counter gets set to an address that's in the data section, the program will crash instead of executing data as if it were code. And if you try to modify the code at runtime, again, the program will crash. Okay, so that's why these are important, to indicate, what is allowed to be executed and what is allowed to be modified as data. So you do need to put those in, or your programs will crash all the time, and you'll wonder, hey, why is this crashing? And they used to not be necessary because operating systems and CPUs didn't enforce this. You could mix code and data all you wanted, but I mean, it's a good thing for security, right, to enforce this. Okay, and I've got a question here. Isn't a char 16 bits in Java? And so how do we, how do we create a literal out of that? So you can, so you don't get a nice sort of string-like syntax for a sequence of 16-bit characters, but DW, so DW, and now you give a number. So let's say 65. So this is going to be a 16-bit word, right? And 65 is the letter A, right, in ASCII. So so DD is for a double word, 32 bits. DW is for a an Intel word, which is 16 bits, right? So if you want a 16-bit constant, use DW, and you're going to have to break up your strings into individual characters with individual DWs. I'm not 100% sure, but I think the NASM assembler allows you to put a character literal in here as well. I'll put I'll put a question mark here. Don't quote me on that, but I think you can put a character literal for DW, so you don't have to output the ASCII codes. I'm not 100% sure on that. Okay, so you just put a sequence of these to get an array of them in memory, one after the other. Okay, and that's so that's the whirlwind tour of the essential parts of x86 that you need to know to generate code for JUICE. So are there any more questions on that? I have lots of lectures on how do I generate code for JUICE in general, but that's the one lecture introduction to x86 assembly language, or maybe it was less than one full lecture. Okay, so any questions? Of course, there's lots of documentation online, and I put links to some of the ones that I thought were most useful on the course website. So have a look at those links, and if you find other x86 documentation that you find especially helpful, feel free to share it in Piazza, right, with other students. As I said, there's lots of documentation out there. Not all of it is necessarily useful. Some of it is, too much and too overwhelming. Here's like our 3,000 x86 instructions that you'll never need. Others are, maybe specific to certain operating systems or specific to certain flavors of x86. I mentioned the 16-bit, 32-bit, and 64-bit, and there's been all sorts of other extensions since then as well. But anyway, if you find good resources that are not on the course website, feel free to share them on Piazza. Okay, so I'm going to move on to code generation, unless someone stops me with a question. This worker is dying. All right. Maybe I'll change color. All right. Okay, so let me start, very high level. Right, so, maybe you're looking at assignment 5 and you're wondering, okay, so I need to generate code. I get it. I know the instructions. So where do I start? Right? And my advice for where to start is, don't start writing code. Start by having a meeting with your group. Okay. And the very first thing that you should do is plan how you're going to lay out data in memory. So plan data layout in memory. All right, I'll just do in mem. Okay. So, this is really important, and it's especially important for your group to agree, like, where do I find the value of variable X? Or, if I create an object of some class, okay, well, how are the fields arranged, right? Where are the methods? How do I do a cast, right? If I find that object, how do I know whether I can cast it to some class C? All of that, you have to have a plan for where all your data is going to be in memory. So I'm going to, talk about that a lot today, of, how to organize, well, what kind of data you need in JUICE, and what your options are for where to put it in memory. So a lot of the design is really figuring out where things are. Then writing the assembly language instructions that put it there. You just kind of follow that design. But planning here is really important. And when I say plan, I know, okay, yeah, planning is boring. Let's write some code, right? Writing code is the fun part. So, as part of that, write yourself some functions, some some interface in your compiler to implement your plan. Okay, so if I decide, okay, well, I'm going to put variables on the stack at certain offsets, and I'm going to encode those offsets somewhere. Well, don't go through your compiler generating machine language in every little place where you want to read or write a variable. At this planning stage, write yourself a little function, read variable, right? A function that takes a variable as a parameter and returns the assembly language code to read that variable, okay? And another function to write to a variable, and another function to, I don't know, implement a method call, or to do a cast, or and sort of little operations like that. So you plan your data layout, but then you sort of record that data layout in functions, so that both your compiler is easier to read, right? You say, I'm reading a variable instead of move and label and whatever machine language instructions they are. And also, in case you change your mind on your data layout, you can leave most of your code generator intact and just modify the various helper functions that you implemented for the various basic operations and basic data accesses. Okay, so encode your plan, encode in access functions. Okay, and then step two, this seems like the obvious part, and it probably seems like the fun part, but it's actually the boring and easy part, once you have the plan, this will kind of be obvious, and that's to write code generators for each AST node. And I'll say recursive bottom up. Okay, so the idea is you go through your AST, and for each kind of AST node, right, so you have all your different kinds of expressions and your if statements and your while loops and so on. So for each AST node, you implement a function that generates code for that AST node, right? So, for your if statement AST node, it's going to do some of these conditional jumps. And for your arithmetic, it's going to do those add and subtract instructions. Okay, and this code generator should be recursive. So when you're generating code for an AST node, well, you probably want to first go to its child AST nodes and generate code for those, and have the values that the children compute, get them in the right registers and arrange them so that after those values come out of the child nodes, they're in the right registers for the operation for the current AST node. Okay, so it's basically a template, a bit of assembly language code for each AST node, and I'll talk about those. Not today, in the lectures next week, right? About some of the templates, some of the bits of assembly language for the AST nodes, and it kind of feels like the exciting and the fun part, but it's really the planning, the data layout that's crucial to make this second part successful, right? To make all the AST nodes fit together and communicate with each other, and to make your group members, right, communicate with each other. So I think I'm stressing this enough, but especially on part one, like, have a meeting, talk to your group members, write down your data layout, it can be part of your assignment 5 report, right? You can write it down in rough form and then turn it into the report. Like, tell me, what's on the stack, what's in the heap, how are objects organized, how is the stack frame organized, where do I find the variables, stuff like that. And I'll just mention a third step, which is optional. So this is to write supporting runtime code. Okay, so I had a question earlier about libc, right? So, when I compile a C program, if it has a printf in it, the compiler doesn't go and generate assembly language code for printf. It just generates a call to a printf function, and then there's a library that has an implementation of printf, right? And I mean, when you're actually running things, that library is already compiled. Originally, it starts out as source code. But the point is, typically, not all of the code that you get out of a compiler is necessarily, generated right then and there. Some of it is a pre-written library. So depending on how you implement your code generation, you might decide that some things would be easier if I were to implement them in a little library of assembly language functions, and I would just have the compiler generate some calls to those functions. So, and I mean, I already talked about this runtime.s, right? So partly this is a start of such a runtime library. And for many groups, the runtime.s that I give you is enough, and you don't need to implement any more runtime code. But again, depending on how you choose to implement the various features of Juice, some of them you might implement by a call to some assembly language code where you're going to write that assembly language code separately, and it'll be part of your runtime library. Okay, so this is a part. Your compiler can still generate this code in the sense of outputting it, but you would have a library, hard coded into your compiler as a string, or you can, write as a file and have your compiler copy that file and put it in with the code that it outputs. Okay, but this is like a constant piece of assembly language code that your generated code might want to call. All right, and again, it depends on the complexity of the language. For Juice, you probably won't need this, but you might find it easier to implement some things this way. Okay, so planning. Planning is important. Planning data layout, right? So how am I going to lay out my data in memory? Well, let's look at what data we need to lay out, right? So what data is there in Java? Okay, so, and do stop me if there's questions. Java data, right? So data, okay. Okay, well, to implement a Java program, what do I need? Well, of course, there are local variables. Right, so I'm going to need to implement those somehow. And, this is, if we were in person, I would ask you to brainstorm, tell me all the data that you have floating around a Java program at runtime. But I mean, objects, right? So objects, obviously, Java is an object-oriented language. You create objects every time you say new foo, right? So objects are kind of an essential piece of data in Java. And all right, so what's in an object? Well, so in an object, I have values of all the fields of that object, right? So the fields of an object are a little bit like local variables. They're areas of memory that hold values, right? And they're named just like local variables are named. All right, what else do I need in an object? Well, you know, I talked about Java being statically typed and dynamically typed. And so every object has a runtime type, right? And so every object needs to know what its runtime type is. Like, am I an orange or am I an apple, right? Can you put me in an array of oranges? So the way I'm going to represent that in an object is as a pointer to a class, and this is the tag, right, of the object. This is the runtime type of the object that allows me to say do a cast or an instance of test and so on. Okay, and the way I'm just going to implement it with a pointer, so just an address of, you know, some other data structure that's going to keep track of all the information about the type of an object. And so that means that in addition to objects, I'm going to have classes, right? So for each class in the program, I need a data structure at runtime that represents that class, that all the objects of that class can point to. And I need enough data in this class to be able to do things like type tests, right? So inside a class, I'm going to have subclass testing data. You know, so like if I have an object and its runtime type is apple, and you do an instance of fruit, I need enough information about apples to know that they are a kind of fruit, right? To be able to implement the instance of test at runtime. Okay, so that's the subclass testing data. I'm going to need to encode that in a class. What else is there in a class? Well, static fields, right? So in objects have fields, but classes can have static fields. So these are fields whose value is sort of global to a specific class rather than individual to object instances. So I'm going to have the values of the static fields in the memory for the class. And what else do I need in a class? Well, you know, if I have my apple and I call the .eat method on it, or you know, whatever method you would call on an apple. So, you know, I mean, depending on the runtime type of the object, I might call a different implementation of whatever method I'm calling. So I'm going to have the addresses of, so pointers to method implementations. Right, or method bodies. So, you know, an apple can have a different eat method than an orange, say. Okay, and so I'm going to have those, but all apples have the same implementation of all their methods. So I'm going to keep this information about where I can find the code of each method in the class, and then an object points to its class, and a class points to the method implementations. So by dereferencing a couple of pointers, I can find that the eat method on whatever object I happen to have. Okay. So this is the information that I need for classes, and finally for arrays, or I guess the last piece of data that I need in a Java program are arrays. And so, I mean, what's in an array? Well, an array has a length, right? You need to know how long the array is to do bounds checks at runtime. And then, of course, the actual elements of the array. And one thing that you might forget is that you also need a type tag. So also a pointer to a class. So, I mean, it's not really a class, but it's a representation of the runtime type of that array. So I'll say tag here as well. So a pointer to one of these data structures that knows how to do subclass testing. I guess in this case, it doesn't have any static fields, but method implementations. So an array has all the methods of Java Lang object, so you need pointers to those implementations, even for an array. So the point is, an array and an object need to have a pointer to the same kind of type info as, they both need a pointer to one of these little class data structures, right? That lets you do subclass testing and that lets you call methods. Okay, what about calls through interfaces? Well, yeah, so we're gonna need to, okay, so this is just a list of all the data that I need to have, right? Like later on, we need to go into this more in more detail, like, how do I actually lay out objects so that I can generate code to access a field? Or how do I lay out a class so that I can find the methods of that class, right? So if I have an object and, let's say I'm see a method call, statically in the Java program, there's a call to some method. And maybe it's an interface method, right? So maybe statically, all I know is that is that I have an object whose class implements the method, whose class implements the interface, fooable, and the interface fooable declares a foo method. And now I need to figure out, okay, how am I going to, I don't know what object it is. I don't know even the runtime class of the object. All I know is that it will be one of the classes that implements that fooable interface. And now I need to implement a call to the foo method of whatever object it is. So what kind of information and how do I need to organize the information in my object? And then it's going to have a pointer to its class. So then how do I get enough information in the class to be able to call, to be able to figure out where in memory the implementation of the foo method for this specific class of object is. Okay, so we're going to have to go into the details of this, right? Of how to organize objects, how to organize classes, how to organize arrays and local variables. Okay, so I will go into details, but not until like Monday, right? So, well, yeah, no, for these, not until next week. Okay, so one, I've got the Java data that I need to store, and now, I'm going to store it in memory. So what's memory, right? What options do I have in memory for storing all this data? Right? And actually, all right, let me erase this part too. Before I go into memory, one other sort of Java consideration is the various data types. right? So data types. And, depending on the data type, they require a different number of bits, right? So an int in Java is 32 bits. And then you've got short and char that takes 16 bits. And then you've got byte that takes 8 bits, and Boolean that takes 1 bit. And then, one thing that is actually kind of nice about Java is that objects and arrays, everything else is always passed by reference. So I can just say reference is 32 bits. Obviously, the object itself is going to take more than 32 bits, but in Java, you always pass it by reference. You never copy it by value. So what you need to put in, say, a local variable or in a field is just a reference, and that's always a fixed size of 32 bits. That actually makes compiling Java much easier than other languages like, say, C, where you would have every struct would be a different size. So, but I mean, we still have a bunch of different sizes here, right? So, if I have a local variable and it's a Boolean, do I want to implement it with just a single bit of memory? Well, I mean, okay, that would be efficient, right? That would make good use of memory. But it's also really painful to say, okay, I have this method here, and maybe it has 4 Boolean variables, so I'm going to generate code that's going to pack them into 4 bits, inside some byte. Saves a lot of memory, but generates really complicated code. So what I would suggest, I mean, all these numbers are all pretty close to 32. So just use 32 bits for all data types. Okay, just to keep things simple, right? So every value will be 32 bits, and for some types of values you won't use all 32 bits, but it's just going to be easier to keep track of where things are if every value is the same size. Okay, this doesn't work for all languages, right? For some languages, I mean, an object could be an arbitrary size, and you might need to store it by value, and so you might need to have a variable amount of memory for a given variable, right? If it stores an object of some unknown size. But in Java, the easy thing to do is just use 32 bits for everything. You don't have to. You can go and try to optimize things. Only use 16 bits for a short or a char. It's going to make it, harder to do assignment 5. But I mean, it's your compiler, your decisions. So if you want to do that, that's great, and you can talk about it in your assignment 5 report. Okay, but I've got all this data, and now where can I put it in memory? So storage options. Well, all right. Well, what do we have here? So I can encode constants in the generated code, right? And either the thing I talked about earlier, I can create a labeled memory location, and then I can put a constant like with the dB or dw. So in this case, I'll put the string hello at a labeled memory location in the generated program, and then I can access that constant from my generated program. Or I can encode constants as part of instructions. So let's say my Java program has the constant integer 42, well, I can generate, in my generated code, I can generate a move instruction that loads the constant 42 into a register. Okay, so constants are sort of the simplest piece of memory, but they're constant. You can't change them. Registers, right? I can put stuff in registers. And the thing to keep in mind about registers is that I have a limited number. Okay, so if I decide to put, say, local variables in registers, I've got to be careful because I only have like 6 or 8 or however many registers. And so if my Java function has 10 local variables, I can put some of them in registers, but not all of them. So I'm going to need a backup strategy for if I have more variables than there are registers. Okay, another place in memory is a fixed memory address. Okay, and so again, that's kind of like what I talked about here, where you put a DW, you label it, but you put it in the data section, and then you can change it at runtime. So you have a memory address that's dedicated for a certain piece of data. It's got a label so that you can access it in the code, and you can store stuff there. Then you might want to use a stack, right? And typically we would store things at fixed offsets from the top of the stack or from some stack pointer. And so this is good for data that you create in a last in, first out order, right? Because that's how stacks work. You push things on them, and then you pop the last thing you pushed first. So any data that kind of follows a last in, first out order makes sense on the stack. And then some data, you're going to need more flexibility. So a heap data structure allows you to allocate and free data in any order. Okay, so at a high level, this part of planning how I'm going to lay out my data, right? You want to do it in more detail than just this, but just the high level, non-detailed thing is to take the stuff on this board and the stuff on this board and like match them up, right? To say, okay, where am I going to store my local variables in memory? Where am I going to store my classes in memory? And so on. Okay. And then, once you have the general decisions, then go and figure out, okay, well, within that piece of memory, what order do the variables go in? Where are the fields? Where is the pointer to the class? And, fill in the details. But at a high level, it's just, local variables, which of these things, do I store them in? And, there's no sort of absolute right answer. Partly it's your decision. You can choose to store your local variables on the heap and it will work. It's a pretty unusual way to do it, but it is a possible decision. What I'm going to give you now, I have like 1 minute left, but I'm going to give you some suggestions of the easiest way to implement these decisions. But feel free to deviate from them, right? Feel free to organize your memory differently. Okay, so local variables, at least in Java and Juice, get created in a last in, first out order. And so, sort of the standard and simplest way to implement local variables is to put them on the stack. Okay, I guess I'll have to go green then. My red pen is not working. All right. So there we go. Lots of compilers will try to put them in registers. And if you do that, that's great. That will generate even better code. The problem is there's a limited number of registers. So if you implement variables in registers, you also need a backup strategy. And then typically your backup strategy is going to be the stack. And once you have the backup strategy, a compiler with one strategy is simpler than a compiler with two strategies. So in terms of ease of implementation and ease of getting assignment 5 done on time, the stack is your easiest bet. Okay, so objects. Well, so the thing about objects is that you don't know at compile time how many objects are going to be created when the program runs, and you don't know when they're going to be created. So objects pretty much have to be on the heap. And same thing for arrays, right? Again, those could be created at runtime. Okay, and so that leaves classes. And for classes, there's some things like static fields that, whose values change. But at compile time how many static fields you have, right? You can make a list of all of your classes, and for each class, a list of all of the static fields in that class. And so you can make a global list in your compiler before your program even starts running of all the static fields that you need to implement. So then the simplest thing to do to implement those static fields is, for each static field, generate a label, and in your generated code, reserve a memory address for the value of each static field. And then you can, really easily generate an access to a static field. It's just a read of a fixed memory location. Okay, so for static fields, the easiest thing, put them at fixed memory addresses. And then finally, for the pointers to method implementations and sort of the subclass testing data, so I'll connect them here, they're also known at compile time, but, even more than that, they are constant. So, in your compiler, right, before your program even runs, all the information about subclasses, and where you're going to generate the code for the implementation of each method of each class. So you can encode that information as constants in your generated code. So you put some dB or DWs with some labels that store all of this information. So you can put that as constants into your code. So there's, let's see, I'll stand off to the side here. So the lines that I've drawn, those are, sort of my suggested layout as sort of the easiest design, but it is your compiler, and you can lay things out differently. So you can, make different decisions here, either to get more efficient code, or, maybe you think something different is going to be easier. Okay, so that's the sort of the high level layout. Next week, I'm going to talk, about more details of the layout, like how you might want to lay out local variables or objects or things like that. So we'll talk about that next week, and also the code generation for the various AST nodes that you might have in your compiler. So I'm going to leave that to next week. Are there any final questions about sort of the overall data layout? Sorry, I'm not sure where exactly to stand, right? Maybe I'll stand over here for a bit. I've been standing over there for a bit. Okay, so any last questions about the overall layout? Okay, so as I said, meet with your group, make sure you agree where things are, and especially at the high level, but also the detailed layouts. So questions, 5 seconds for questions. Okay, so have a good rest of the week, have a good weekend, and we'll continue this on Monday. Okay, bye.